All right, let's dive in. Today, we're tackling one of the biggest ideas in chemistry, ionic bonds. This is all about how atoms team up in, well, a pretty dramatic way by giving and taking the one thing they need most. But first, let me ask you something. Have you ever really looked at a tiny crystal of table salt and wondered why it's so solid? Why it's a hard little crystal and not just, dust? Well, the answer is an incredibly powerful invisible force holding it all together, and that is exactly what we're going to uncover today. So to get this, we first need to understand the problem that pretty much every atom has. See, deep down, all they really want is to be stable. They want a full outer shell of electrons. That's their happy place, their most stable energy state, kind of like the noble gases, which are super chill and unreactive. But most atoms, well, they don't start out that way. You could say they're a little bit unstable and unhappy. And this brings us to the two main characters in our story. On one side, you've got the metal atoms. They've got just one or two electrons in their outer shell, and honestly, it's way easier for them to just get rid of those to reveal a full shell underneath. And on the other side, you have the nonmetals. Oh, they are so close to having a full shell, they just need to grab one or two more. They have completely opposite goals, right? But that's what makes them a perfect match. So, what's the solution to this whole atomic dilemma? It's not a big fight. It's actually a deal. A metal atom and a nonmetal atom can team up and solve each other's problems through one simple, brilliant move. Let's look at the classic example, making good old table salt. So you have sodium, a metal with one lonely electron in its outer shell that it is desperate to ditch. Then you have chlorine, a nonmetal that's just one electron away from a perfect set. So what happens? That electron doesn't get shared. No, it literally jumps from the sodium atom right over to the chlorine atom. Just like that, both atoms get exactly what they wanted. But here's the thing, this electron swap changes them in a really big way. You have to remember, electrons are negative. So when that neutral sodium atom loses a negative electron, it's left with more positive protons. So it becomes a positively charged ion. We call that a cation. And on the flip side, when the neutral chlorine atom gains that negative electron, it becomes a negatively charged ion, which we call an anion. Okay, so the electron has moved, both atoms are now stable ions. You might think the story is over, but it's not. In fact, the most important part is just about to happen. This transfer creates an incredibly powerful new force. And here it is, the absolute heart of the matter. We now have a positive sodium ion and a negative chlorine ion. And we all know what happens with positives and negatives, right? Opposites attract. This incredibly powerful electrostatic force, think of it like a super strong version of static cling. Between that positive cation and that negative anion is the ionic bond. That's what holds them together so tightly. Let's just put a formal definition on that to lock it in. This really nails the two-step process. First, the complete transfer of electrons, which makes those oppositely charged ions. And second, the super strong attraction between those new ions. That's it. That's an ionic bond in a nutshell. Now, this whole process doesn't just happen between one sodium and one chlorine atom. In the real world, we're talking billions upon billions of these ions all coming together, building this massive, super organized, and incredibly strong structure. And that amazing structure has a name, the giant ionic lattice. Don't let the word scare you. Giant just means it involves a huge number of ions, and lattice is just a fancy way of saying a regular, repeating 3D pattern, kind of like a perfectly built crystal scaffolding. So how does this lattice get so strong? Well, inside, every positive ion isn't just attracted to one negative ion. Nope. It's completely surrounded by negative ions, pulling on it from all directions. And likewise, every negative ion is surrounded by positive ions. This creates this incredible web of forces, making the entire structure ridiculously strong and stable. This is why salt is a solid crystal at room temperature. Okay, so this is the crucial link. That tiny microscopic lattice structure gives ionic compounds some very distinct and predictable real-world properties, or as I like to call them, their superpowers. Superpower number one, super high melting points. I mean, to melt an ionic compound like salt, you literally have to break apart that super strong lattice. Those electrostatic forces are so powerful that it takes a massive amount of heat energy to get those ions to vibrate enough to break free. That's why you can't melt salt on your stove. All right, on to the next superpower. What about conducting electricity? Now, to conduct electricity, you need two things: charged particles, and those particles have to be free to move. We've definitely got the charged particles, our ions, but are they free to move? Well, the answer is, it depends. When it's a solid, those ions are locked rigidly into place in that lattice. They can't go anywhere, so solid salt cannot conduct electricity. But, and this is a big but, if you melt it or you dissolve it in water, the lattice breaks down. The ions are now free to move around and carry a current. So yes, they can conduct electricity, but only when they're melted or dissolved. Okay, a couple of other key properties to remember. Ionic compounds are very hard because of that strong lattice, but they're also brittle. If you hit a salt crystal with a hammer, it shatters. That's because you shift the layers, forcing ions with the same charge to line up right next to each other. They repel like crazy and the crystal breaks apart. And yeah, many of them, like salt, dissolve really well in water. So let's do a quick recap by comparing ionic bonds to their cousins, covalent bonds. For ionic, the key word is transferred. Electrons are transferred from a metal to a nonmetal. This creates that strong lattice, giving them those high melting points and that ability to conduct electricity, but only when the ions are mobile. This is completely different from covalent bonds, where electrons are shared between nonmetals, which usually means lower melting points and no conductivity at all. And we'll end with a little something to chew on. We've established that the force holding an ionic lattice together is this powerful attraction between opposite charges. But if that pull is so incredibly strong, what stops the positive and negative ions from just crashing into each other and collapsing the entire structure? It's a great question, and the answer leads to an even deeper understanding of how all these atoms work. Thanks for tuning in.